race for space.
World's first 3D printed rocket.
Rockets built and flown in days instead of years. That is the mission at Relativity.
Relativity. Relativity.
Welcome back. Thank you for joining us again from Cape Canaveral Space Force Station in Florida, where we are preparing for our second attempt at launching Terran 1, the world's first 3D printed rocket. Today's flight is named Good Luck, Have Fun, or GLHF for short. This is Relativity's first launch. We'll be bringing you live coverage from Launch Complex 16, which is our launch pad here at Cape Canaveral, as we prepare for historic liftoff. I am Rachelle Aniceto, the Chief of Staff for the Vehicle Architecture and Technology team at Relativity Space. I support our Chief Architect, Kevin Wu, in the design, development, and product management of our medium to heavy lift reusable launch vehicle, Terran R.
And I'm Arwa Tazani-Kelly, Technical Program Manager for Test and Launch at Relativity Space. I'm responsible for supporting the teams that design, build, and operate our test and launch sites across the country for both our Terran 1 and Terran R vehicles, including operations on the stages, engines, and propulsion components. Together, we'll be guiding you through our second launch attempt today. Now, if you joined us on Wednesday during our initial attempt, you know we ultimately decided to scrub due to propellant conditioning issues. Before we get underway today, we want to share a bit more detail and explain how it impacted our first attempt. During Wednesday's operations, a ground equipment valve was malfunctioning. This prevented us from having adequate control over achieving the cold temperatures we aim for with our liquid oxygen. The team has since fixed this valve and incorporated additional mitigations to get that liquid oxygen, or LOX, to remain at acceptable temperatures. Additionally, we've seen questions about why we opted to schedule our next attempt today as opposed to going again on Thursday. The team was able to quickly repair that ground support valve, so that wasn't the cause for the delay. Instead, it had to do with our propellants. For those of you less familiar with Methalox propelled rockets, our liquid natural gas is mostly comprised of methane. But there's also a little butane, ethane, and propane, which are higher order hydrocarbons. As such, methane, being the simplest molecule, boils off faster, lowering its concentration over time. When we load propellant, we do so in a way that achieves our optimal methane levels. If we were to offload and reload those same propellants after a scrub, our methane composition would be off. Instead, we bring in fresh propellants, and the fuel then needs some time to level off to the right compound mix before we make another launch attempt. The good news is that propellant loading is proceeding smoothly today with no reports of issues with our valves or our propellant temperatures. Now we're currently at T-minus 50 minutes and counting. I did just receive confirmation that propellant loading is wrapping up for both stages. The range is green and the vehicle is healthy. However, we're keeping a close eye on upper level winds right now, since earlier forecasts were indicating marginal conditions for today's launch attempt. We use a combination of data from global forecast system modeling and real-time data from our weather balloons, which we are releasing periodically. We do this to determine if enough thrust vector control, or TVC margin, is there to overcome the atmospheric wind shear as Terran 1 approaches max Q. While winds at ground level today are acceptable for launch, remaining between 15 to 20 miles an hour, the upper level winds could impact our ability to gimbal the engines enough to keep us on course for our intended orbital trajectory. Current data is indicating we are a go for launch, but this is something the team is continuing to monitor.
Thank you, Arwa. Arwa will provide regular status updates over the course of the countdown. In the top left of your screen, you can follow our countdown clock to help follow along in our pre-launch operations.
Thank you, Rochelle. And now a quick reminder about the purpose of Good Luck, Have Fun. This is a first launch, meaning that while we're aiming for Terran 1 to reach orbit, our primary focus is on gathering the data and learnings necessary to develop Terran R, our much larger medium to heavy lift reusable launch vehicle. The lessons learned from this mission will also enable us to improve our software-driven approach to manufacturing.
And today's launch includes many firsts. Terran 1 is the first 3D printed rocket, which is 85% 3D printed by mass. It's in a race to become the first methalox-propelled rocket to achieve orbit. And if orbit is achieved, Relativity will also become the first venture-backed space company to have successfully reached orbit on its first flight.
And it's worth noting that while Terran 1 will be capable of lifting 1,250 kilograms into low Earth orbit, or LEO, today's launch doesn't have a customer payload. We do, however, again, have a Memento on board, one that's quite unique to Relativity that we'll tell you more about later.
So liftoff is currently scheduled approximately 48 minutes from now. This estimation may change as we work through our countdown. We will keep you updated along the way. Today's launch window lasts for 3 hours. This gives us time to troubleshoot any issues. If there are any unforeseen issues during the countdown, we can pause the launch sequence if necessary.
And as we await our first launch, let's take a minute to reflect on the path to this historic moment. In just 7 years, we've gone from an idea on the back of a coffee receipt to the 1,000 plus full-time employee company we are today.
Hi, I'm Tim Ellis. I'm CEO and co-founder of Relativity Space.
I'm Jordan Noon. I'm CTO and co-founder of Relativity Space.
And we are building the world's first fully 3D printed, robotically assembled rocket launch vehicle.
It's called Relativity Space. It's happening at a young startup called Relativity.
Startup in LA's aerospace hub that's on a mission to completely 3D print a rocket.
They're going to launch over there at the Cape Canaveral Air Force Station with a rocket that they are printing with the world's biggest 3D printer.
Starting Relativity is a pretty big adventure. We wanted to be the first company in the world to 3D print an entire rocket, and I really felt this was inevitable. It's just myself and Jordan Noon. I was 25, I think he was 22, so we were getting an early start at building this thing. What's amazing is I actually have a photo of a Starbucks receipt where we wrote out the original vision of Relativity. Really, we knew building our own 3D printers, which had to be the world's largest 3D printers, was one of the first things that we had to figure out. So we spent the first couple of years really refining that technology, just frankly figuring out how to build a finance team, get customers, get any traction at all, really, just to start to breathe life into this vision that we were building towards, and having those first employees really start to define the values and culture of Relativity. Our first engine tests, our first igniter tests, our first Stargate prints of full-scale hardware, and man, I'll tell you, some of those early prints look like piles of metal and pretty crappy, so we really had to figure out how to refine the technology. Those early days, there were a lot of hard-won battles, but we learned really, really quickly and really started to hit an inflection point about 3 years ago. Sending that email to Mark Cuban, I just felt we had absolutely nothing to lose. 3D printing is the future. I really feel so lucky that we live in a special time where we actually have the tools, the momentum, and the ability as a company and as an industry leading humanity's future in space. This is the year we're doing it. We've got tons of great team members working on it every single day, and I believe it's a challenge for any team, but for our team, we've got nothing to lose. So I'm very excited and humbled by the people that have joined us and what it means to actually build this thing together.
We often get asked, what is Relativity Space? Well, let me tell you, we are a rocket company. We build rockets designed to offer high performance and reliability while costing less to build and fly. This lets us put our customers first. Our long-term vision is to expand the possibilities for the human experience by creating humanity's industrial base on Mars. Our rockets, Terran 1 and Terran R, have already been met with significant market interest. To date, Relativity has announced nearly a dozen signed customers for commercial and U.S. government payloads. Some of our customers include OneWeb, Iridium, NASA, and the Defense Innovation Unit. Currently, Relativity's customer contracts amount to more than $1.65 billion. We are a private venture-backed company, and to date, we have raised over $1.3 billion in capital with our most recent $650 million Series E round. This funding has allowed us to make progress on Terran R, as well as get Terran 1 to today's launch. With that, let's take a step back and see how we're tracking towards launch.
We are currently at T-minus 42 minutes. The vehicle still appears to be operating nominally. The weather is looking good so far. We're still keeping an eye on those upper level winds, but other than that, we're tracking well towards a 1300 Eastern Time launch.
That is great to hear. Good luck, have fun is the maiden launch of our 3D printed Terran 1 rocket. Terran 1 is an orbital class rocket, and of course, reaching orbit would be a total home run. But as we've mentioned before, we're just truly looking for some important base hits here today. Notably, a key objective for today's flight is largely about proving our hypothesis that 3D printing is a viable way to manufacture a rocket, and it can successfully withstand the pressures of flight. Through robust ground testing, we're confident that we have a real shot at proving just that. And the more data that we collect from this first flight means that we'll have access to more insights. And this will give us the confidence that we're able to execute on Terran R. And it will help us solve all the hard problems that come with building a medium to heavy lift reusable rocket. As a business, we are following the Pathfinder product development approach. So the Terran 1 that you see on the pad today has always been our Pathfinder. It was designed to be a development platform for Terran R, and it has served us exceedingly well to date in that capacity as we've progressed through printing and testing ahead of today's launch. Arwa, what would we call success for today's launch?
Well, again, safely clearing the pad, getting out over the ocean, and passing the point of maximum dynamic pressure, or max Q, would be a big inflection point for today's launch. This is because it's the point where the structural loads on the vehicle are the highest, making it one of the more challenging phases of flight. This is the point in flight where we want to prove much of what has already been proven on the ground. During acceptance testing, the vehicle withstood loads even beyond what we anticipate it will encounter during flight. So passing this milestone would effectively demonstrate that 3D printed rockets are structurally viable. If we make it even further to stage separation, we will have achieved a full first stage flight. And that'll be another big accomplishment for the team. From there, we'll attempt to light the second stage and get Terran 1 to orbit.
So at that point, it's going to be so tough not to jump out of our seats if we get to that point. Just as a reminder, Stage 2 is targeting a 200 kilometer by 210 kilometer orbit, which is not a traditional orbital target. However, that is our target for today, given that this is our first launch and not a customer mission. There is no customer payload on this flight. Instead, to celebrate how far we've come, we have mounted our first ever metal 3D print from the first generation Stargate printer inside of Terran 1's nose cone. And while we're on the topic of setting expectations, we will also note that we are unsure how much of the second stage flight we will be able to share with you live. While we do have cameras on board, we will be prioritizing vehicle telemetry sensor data for this launch in order to maximize our learnings. And as a result, the video connection could be spotty. So in the event that we do lose video, we will do our best to keep you up to date as we receive telemetry.
And I just want to update here that our launch time is set now for 13:45 Eastern. We have updated that with the range, and you can follow along on the time clock on the top left-hand corner. We do have strict safety protocols in effect for today's flight and are closely coordinating with the FAA and Space Launch Delta 45. These protocols are standard for all launches and ensure that no one would be in harm's way if there were to be an anomaly. The window for today's launch attempt opened at 1300 Eastern, and it lasts for 3 hours. The pad was cleared of all personnel again at T-minus 4 hours, followed by the start of propellant loading. Propellant loading is now nearly complete, and we're going to top off our tanks and condition our propellant shortly. At approximately T-minus 20 to T-minus 15 minutes, the launch director will poll the launch teams to ensure that all subsystems, weather, and the range are go for terminal count. Terminal count will then begin at T-minus 70 seconds, and that's when the vehicle's internal flight computer takes control of the countdown. Now, while we wait for T0, let's talk about the process that got us here once again. Terran 1 is 85% 3D printed by mass. The items that aren't 3D printed include rubber seals, computer chips, valves, and other similar items. We see 3D printing as an automation technology, and we believe that long-term 3D printing will rapidly democratize space. We've already been able to unlock rapid part count reduction and rapid design iteration, and we're still very much in the early days of what's achievable. Now, we use 2 classes of printers here, powder bed fusion, or PBF, and vertical wire arc additive manufacturing, or WAM.
For those of you that are tuning in today for the first time, powder bed fusion, or PBF, is a process that uses a heat source such as a laser to sinter or fuse together particles in a layer-by-layer process. Let's show you an example of a PBF printed part. What you might see on the screen right now is a development part. Specifically, this is a development part that we use for our Aeon R engine. It's an example of a turbopump housing. We use PBF to print our 9 Aeon 1 engines and the single Aeon vacuum engine on the second stage for Terran 1. We have been able to increase reliability through lowering our part count with PBF.
And now let's maybe pull up an example of one of our WAM development articles. Our proprietary Stargate printers use WAM for printing the vehicle structure. We developed a proprietary metal alloy that begins in a wire spool and is then fed into a Stargate printer. It's then heated and cooled rapidly to form small beads that, in succession, create the vehicle structure, layer by layer. That includes the Stage 1 and Stage 2 tanks that hold the propellant, their internal ribs, the common domes, and of course, the nose cone. This is essentially what makes up the bulk of the visible part of the vehicle on the pad, except now it's painted white instead of the native silver that you see here. Now, I do want to mention that Terran 1 was again vertically printed using our 3rd generation printer, but our 4th generation printer will move horizontally to increase print sizes for our next and much larger vehicle, Terran R. But of course, first, we have to launch Terran 1.
That is right. We have to launch Terran 1 today. So for those of you that missed Wednesday's broadcast, let's do a refresher about the Terran 1 architecture. As a reminder, Terran 1 is 110 feet tall with a 7.5 foot diameter. Starting from the left-hand side and the bottom of the vehicle, there are 9 Aeon 1 engines. Each of these engines has a thrust capability of about 23,000 pounds at sea level. This gives us a max total liftoff of over 200,000 pounds. The Aeon 1 engine is designed with a gas generator cycle. We have thrust vector control actuators, or TVCAs, on the engines to gimbal the engines during flight. We have completed more than 2,000 engine hot fires, and with 10,000 seconds of runtime across the 191 Aeon 1 hot fire tests. The 9 Aeon 1 engines are attached to the vehicle through the thrust structure. This is what takes the loads from the engine thrust. And above the thrust structure is the stage with the WAM printed tanks that Arwa just shared about. This holds liquid oxygen on the top tank and liquid natural gas on the bottom tank. These tanks are pressurized using an autogenous pressurization system. We tap off a portion of the propellant from the engine, and this is run through heat exchangers that are mounted on the engines. The liquid propellant is converted into a gaseous state, and then this is piped back into the top of the tanks to maintain our required tank pressures. Above stage 1 is the WAM printed interstage, and this holds our stage separation mechanisms. For stage separation, we use a pneumatic pusher system. And above the interstage is stage 2, which has a single Aeon vacuum engine. This engine has a thrust capability of more than 25,000 pounds in vacuum and has the capability of multiple restarts. Stage 2 also has WAM printed tanks just like stage 1. And above stage 2 is the WAM printed nose cone. For future missions, this would be replaced with a fairing and also have a fairing separation system. As we mentioned, there is no customer payload for today since this is our first launch, but we did design Terran 1 with a payload capacity of 1,250 kilograms to low Earth orbit, or LEO, and 900 kilograms to sun synchronous orbit, or SSO, for customer missions. All data from Terran 1 development will be fed into Terran R. But our Terran 1 rocket is only part of the formula. As we get closer to liftoff, Arwa, how about another status update?
Yeah, of course. We are now at T-minus 31 minutes and counting. We're not tracking any current weather violations. As I said earlier, we're still going to keep an eye on those upper level winds, but the range is still green and the vehicle systems are still nominal. So as of now, we're still a go for our scheduled launch time. Now for our new viewers, here's a little more info about the systems you're seeing on the pad. The rocket rolls out of the hangar horizontally and is then lifted vertically by the transporter erector. This is the black vertical truss structure you see there behind the rocket. And then you'll also see 4 large towers surrounding the pad that make up our lightning protection system. They protect the vehicle from any direct lightning strikes. Inside of those, we have 4 much smaller black posts called rainbirds. They're used for acoustic mitigation for the rocket and do so by covering the pad with water to dampen the reflected acoustics at liftoff. The small flame you see at the bottom right of your screen is the flare stack. No need to worry there, this is intentional. It burns off flammable gases from propellant loading, venting operations, and priming of the engine igniters. It's a little harder to see here, but there it is. The small slide-looking structure beneath the vehicle is our water-cooled flame diverter. It's used to mitigate the heat from lighting the engines, and it directs the exhaust plumes away from the vehicle. You'll also see what looks to be 3 different levels under the rocket. The largest and lowest level is the pad deck, and directly above it is the launch table. This is where the launch mount pins to the pad and creates that flame duct. The launch mount on top of it is one component of the transporter erector. It transfers loads into the pad deck during hot fire tests and engine ramp up at launch. It also contains the release system, or hold downs, and the quick disconnect, or QD carriages that provide propellant and other commodities to the vehicle while it's on the ground. And once again, a big shout out to the ground crews out here for all of their hard work. They've helped us build and operate this launch infrastructure and supported vehicle integration and testing. And of course, they helped us prepare for today's second attempt. So thank you all so much for your incredible work.
These teams have also supported our rigorous test campaigns. Let's go ahead and take a look at Terran 1's journey to launch. Now, as we approach T-minus 25 minutes, we're going to stand by for a situational briefing from the launch director, Clay Walker, in Mission Control. Let's go ahead and listen in.
If you're just tuning in, we are now awaiting a situational briefing from Clay Walker at around T-minus 24 minutes. I'm hearing here that the team is looking into those upper level winds before we proceed with the situational briefing. We should have an update here in just a few minutes.
Announcement on countdown net is the LD. We're holding the clock at T-minus 20 minutes due to upper wind violations. Stand by for a new T0 time.
And as you just heard from Clay, the team is going to hold at T-minus 20 minutes. We're going to continue evaluating those upper level winds and get a new T0. White clouds that you see coming out of the rocket are due to venting of the chilled gas from the rocket into the humid Florida air out here. That's why the gas condenses into vapor and looks like clouds when it's coming out. For those just joining us, we are at T-minus 20 right now, and we're actually holding the clock due to upper level winds. The team is currently evaluating this, and we'll provide an update as soon as they have it. However, the vehicle is healthy and the range is currently green, so as soon as those upper level winds slow down a little bit, we'll be able to provide another update. For those just tuning in, we did hold the clock at T-minus 20 minutes today, but we're expecting a briefing in the next 5 to 10 minutes on what's happening with the upper level winds that were the reason for us holding the clock. We'll continue listening in and hopefully everything sounds good. For those just tuning in, we once again held the clock at T-minus 20 minutes due to weather issues. Unfortunately, upper level winds are currently marginal, so the team is evaluating live data to determine if we can go ahead and keep rolling the clock or if we need to pause for a little bit longer.
And as we wait on that additional data on the upper level winds and as we get an update from the team, let's go ahead and take a moment to get an idea about all the work that the integrated performance team does for Relativity Space.
Hi, I'm Ryan Kraft.
I'm Katie Wallace.
My name is David Brown.
I'm the Director of Integrated Performance at Relativity.
I'm a vehicle simulation engineer.
And I'm a staff vehicle simulation engineer.
One of the key things that we focus on in the department is connecting all the different teams, making sure the structures work with the engines work with the software, and the software works with the electronics hardware. I was lucky enough to work in a few different hardware startups. This is actually number 5 for me. Worked on electric vehicles, race cars, rockets, and manned spacecraft.
A typical day in the life for me at Relativity can vary a lot, but in general, it'll involve running a lot of different trades and analyses, helping with mission planning tasks, and also building up new simulation capability.
I've spent my entire career working on simulation controls. I started off working in the automotive industry on hybrid vehicles, and later moved on to motorsports and general consulting for other industries.
When I saw what was going on at Relativity here about 3.5 years ago, I realized this is the coolest place to be on Earth, and I wanted to join the team. Some of the things that we get to learn every day, I don't think you can learn anywhere else, and the team that I get to do it with just makes it even sweeter. Specifically, some of the big challenges are around figuring out what parts of accepted practice in the rocket industry still make sense for us, and where we should change things, or when we should just throw it out and start over with a completely new approach.
I think one of the most exciting challenges is getting to work on Terran R, especially because our team gets to be really involved with the early design, running different trades and analyses and trajectories. And it's challenging because it's never been done before, but it's really exciting to really get to help shape this new vehicle.
My role is usually involved taking small components and subsystems and integrating them into complex system models, which then have great predictive capabilities. What I find most exciting about this is then taking these models and using that capability to help guide design work.
There's a lot of places where an engineer can come in today and still define how Relativity will do rocket engineering for the next 5 to 10 years. When we look for candidates in the integrated performance team, the main thing that we're looking for is hunger to face really hard problems and excitement to learn as you go. We're just looking for people with different views, different experiences, and different ideas to find the right way to do a reusable rocket next time around.
I think someone who would be a great candidate for Relativity would be someone who enjoys working on complex problems and solving difficult challenges. Having any background with simulation or launch vehicle modeling is always helpful, as well as orbital mechanics or general physics background.
One thing I would suggest for candidates coming from more traditional physics backgrounds is to basically demonstrate that you have the experience of taking the analysis that you've performed on a computer and turning that into actionable insight that you can share with the team and use to help guide design decisions.
Right now the team's about 40. We're looking to double that in the next year or so. We've been growing a lot in the last year, but definitely a lot more to come as we get ready for Terran R and all the fun physical challenges there. One of the very unique opportunities here at Relativity is being part of a lot of technical firsts. We printed our first rocket, we're testing it right now, we're about to go through our first launch, then our first customer, and eventually our first re-entry landing of a booster and reuse of it. One thing that people might not know about working in an integrated performance team in a rocket company is that a lot of us didn't have a rocket background when we came in. People come from cars, software development, engineering analysis, planes, missiles. I feel like the opportunity for a really fast pace of learning across a very broad range of technical topics, you can't really find that anywhere else. I think what draws people to Relativity is it's a unique type of physics.
It looks like we are coordinating a new T0 right now that is going to be at 14:35 Eastern. We're awaiting confirmation from Mission Control at the moment, so we're going to continue listening into them for any further updates. And now the T-clock is rolling again. We are now 38 minutes away from our new scheduled launch time of 14:35 Eastern. Again, that's 14:35 Eastern, less than 40 minutes away. We're now at T-minus 31 minutes, and you might be wondering where we built the launch vehicle that you're seeing on the pad. We currently have 2 manufacturing facilities in Long Beach, California, and today's rocket was printed at our second factory called the Portal, while our new headquarters, named the Wormhole, is home to our 4th generation Stargate printers. This is the 1 million square foot facility we are currently expanding into that will serve as the epicenter for Terran development and production.
Speaking of Terran, Terran 1 is truly a pathfinder to that vehicle. The real opportunity in the market, as proven by our customer contracts. We are actually already ramping up production for this medium to heavy lift reusable vehicle. We have designed it to be capable of 20,000 kilograms to low Earth orbit, or LEO, and we plan to still benefit from the large-scale metal additive manufacturing. One key learning from Terran 1 is with the engines. Let's take a look at this clip of the Aeon R thrust chamber assembly test. So what you just saw there was a full power test of the Aeon R thrust chamber assembly. I want to give a special shout out to Jake Shearman, Senior Manager of Combustion Devices, the Propulsion Test Team, and the Stennis test teams for accomplishing that critical milestone. So full power means 258,000 pounds of thrust at sea level. That is what we are designing Aeon R engine to. And that is 10 times the capability of the Aeon 1 engine that we have on Terran 1 today. We are already well underway testing components such as a full-scale gas generator test, igniter testing, and as you just saw, that full-scale thrust chamber assembly. We are currently building our integrated engines, and on our Twitter feed, you can actually see an image of our first integrated engine next to a human for perspective on size. We are also completing building of our turbopump assembly, and we're planning to go into full engine tests throughout 2023.
And we're going to test those engines over at the NASA Stennis Space Center in Mississippi, where most of our testing is done. In 2018, we secured the first Commercial Space Launch Act, or CSLA, agreement with NASA Stennis. And we now occupy several operational facilities there, including 4 exclusive use test stands for Terran 1 stage and Aeon engine testing, 2 stands used for Aeon 1 engine tests and Aeon R component tests, and 1 cell for Aeon R engine tests. On top of that, we're building out an additional 150 acres for the Terran R program, and we've already started construction on the new engine test stands. Other structures there will include a full-scale second engine stand, office buildings, and of course, an integration hangar. All the structures we're completing out there are built from the ground up on previously unused land. After testing, we ship the components to the launch site. We, of course, have our operational site here at the Cape, but we've also acquired a site in Vandenberg, California, as an additional option for future launches. In 2019, we secured a direct agreement from the U.S. Space Force for Launch Complex 16. And Relativity joins just a few others here as only the 4th company with a currently operational orbital launch site at Cape Canaveral. Both Terran 1 and Terran R will launch from Launch Complex 16. With that, we are now approximately 27 minutes away from launch.
This is so exciting. I hope we continue to move forward. But just as a reminder, we do not have a customer payload on board, but we do have a Memento in the nose cone. We have included our first ever 3D printed piece from our Stargate printer. Of course, it was a failed print since no one had done it before. Let's go ahead and take a look at this Memento. So that piece that you see there is 6.5 inches in diameter and weighs about 3 pounds. It is our first completed circular test article for which we used our first generation aluminum alloy. Since then, we've added a machined centerpiece with a GLHF for good luck, have fun, and our mitosis logo to commemorate this maiden launch.
And from our very first failed print 7 years ago, it's taken a relentless focus on innovation and almost countless iterations to get to where we are today. The world's first 3D printed rocket on the launch pad here at Cape Canaveral. Like the first print, Terran 1 is the first step of many towards making humanity a multi-planetary species. As a reminder, our primary objective for today is to gather as much data as possible to help develop our future vehicles, including Terran R, our larger medium to heavy lift reusable launch vehicle. Now we're currently at T-minus 25 minutes. We're going to continue standing by for further updates from Mission Control.
All parties on net. Situational briefing for pre-go, no-go. All parties be aware the go, no-go poll will be performed in approximately 10 minutes. Primary test objective is a transition into countdown through terminal, startup, and release into flight. Vehicle status, propellant is loaded. We are tracking no additional items for constraints. And while we are still waiting on one final balloon, we are still a go unless that balloon comes back as negative. All assets are standing by for launch, and we will do polls in approximately 6 minutes. Stand by, all parties.
And you just heard that situational briefing from Clay Walker. The vehicle is very healthy right now, and the only issue that we're tracking is unfortunately the weather. But we are awaiting data, the latest data from our weather balloon, to determine if we can continue and go ahead with our scheduled launch time of 14:35 Eastern.
As we continue to wait, maybe let's do a recap on the Terran 1 architecture and go ahead and look at this graphic of our Terran 1 architecture. As a reminder, Terran 1 is 110 feet tall and 7.5 feet in diameter. We have 2 stages that are expendable. On the bottom, we have 9 Aeon 1 engines. Each has a thrust capability of about 23,000 pounds at sea level, giving us a max total liftoff of more than 200,000 pounds. The Aeon 1 engine is designed with a gas generator cycle, and as you previously heard, we have thrust vector control actuators, or TVCAs, on the engines that allow us to gimbal during flight. We have completed more than 2,000 engine hot fires as we prepared going into launch today. The Aeon 1 engines are attached to the vehicle through a thrust structure, and above the thrust structure we have WAM printed tanks. Arwa previously shared that this is the wire arc additive manufacturing in-house process that we use, and these tanks hold liquid oxygen on top and liquid natural gas on the bottom. During flight, we pressurize our tanks using an autogenous pressurization system. This means that we tap some propellant from the engines, and this is run through heat exchangers mounted on those engines and converts the liquid propellant into a gaseous state, and we pipe it back to the top to maintain the required tank pressure or ullage pressure. Above the stage 1 tanks, we have a WAM printed interstage, which holds our stage separation mechanisms. This is what we use to separate stage 2 from stage 1 during flight. The stage separation system uses pneumatic pushers. And above the interstage is stage 2, which has a single Aeon vacuum engine. This engine has a thrust capability of more than 25,000 pounds in vacuum and has the capability of multiple restarts. Stage 2 is also WAM printed just like stage 1. And above stage 2 is our WAM printed nose cone, which we just shared about the Memento inside of that nose cone. For future missions, we will replace this nose cone with a fairing and also include a fairing separation system. Terran 1 was designed with a payload capacity of 1,250 kilograms to LEO or 900 kilograms to Sun Synchronous Orbit or SSO. All the data from today's launch and Terran 1 development will be fed into Terran R. But note that
NRC RCS checkouts complete.
We're going to go ahead and pause and listen in on mission control for any more updates. Thank you.
As of now, it seems like everything is on track, and we're going to perform the go, no-go polls in just a few minutes here. So we're going to stand by to listen into mission control.
Copy. parties on all nets. This is the go, no go for launch. Please provide concurrence to proceed into launch with launch countdown go, no go. BC. BC go. BC go. GC1. GC go. GC go. GC2.
GC2 go.
GC2 go. Ground. Ground go. Ground go. AVI. AVI go. AVI go. FTS.
FTS go.
FTS go. RF. RF go. RF is go. GNC. GNC go. GNC go. Flight software. Flight software go. Flight software's go. Prop 1.
Prop 1 go.
Prop 1's go. Prop 2. Prop 2 go. Prop 2 go. Fluids 1. Fluids 1 go. Fluids 1's go. Fluids 2. Fluids 2 go. Loads. Loads go. Loads is go. Rock.
Ranges go.
Ranges go. OSM.
OSM is go.
OSM is go. RC.
RC go.
RC go. Vehicle.
Vehicle is go.
Vehicles go. CE.
CE's go.
C's go. LC.
LC is go.
LC is go. All parties that reported go for launch countdown. Once the clock begins to roll, anyone can call for a hold at any time. If a hold is called prior to T-minus 70 seconds, the T-clock will continue to roll until T-minus 70 seconds, at which point a hold will be automatically initiated. A hold is not possible after T-minus 70 seconds. Any hold call after that time will result in a terminal count abort. Should a hold or a manual abort be necessary, the person calling for a hold or abort should say clearly on comms, hold, 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 or abort, abort, abort. In the event that OSM requires a hold, OSM will initiate the hold command on the OSM GUI and notify the LD and the RC on the primary net.
And you just heard our launch director complete the go, no-go polling with our mission control team. As you heard, all systems are currently healthy. So as of now, we're able to proceed with our scheduled launch time in just about 13 minutes.
Throughout today's live stream, you've been hearing callouts from Mission Control. Now let's take a moment to introduce you to our Mission Control team. As you just heard, Clay Walker, Launch Director, John Wiswall, Launch Conductor, James Harris, Chief Engineer, Elijah Escobedo and Zoe Dickert on Vehicle Controls, Brian Batters, Ground Control, Bill Stack, Ground, Joy Mosdell, Range Control. We also have a few notable members of leadership supporting today's launch, and they are also here at Launch Control with us. This includes our co-founder and CEO, Tim Ellis, our Chief Operating Officer who leads product execution, Zach Dunn, Vice President of Test and Launch, Don Katterbeck, and Director of Cape Operations, Pat Zvatek. These are among many, many others who are making today's launch happen. Let's go ahead and take a moment to wait as we get more updates from Mission Control.
For those curious, you'll be able to see small white pieces falling off the rocket. Not to worry, that is just ice falling off from the frost on the vehicle due to the chilled propellant inside. On the other view, you might have also seen a small flame to the far left of the view, and that is just the flare stack that's used to burn off any flammable gases from propellant loading and venting operations. Once again, those white clouds you see coming out of the rocket are due to the venting of the chilled gas from the vehicle into the humid Florida air out here. That's why the gas condenses into vapor and looks like clouds. In just about 46 seconds here, we will begin our countdown sequence.
T-minus 10 minutes, countdown sequence has started.
And we're currently at T-minus 9 minutes and 45 seconds. In the upcoming minutes, you're going to hear several call-outs from Mission Control as we go through the final pre-launch procedural steps, including the priming of the igniters, final engine checkouts, transporter erector retraction, and getting that final go for launch. Again, we're now pressing the tanks to flight pressures, as you just heard, and we're currently proceeding with our scheduled launch time. In just about 30 seconds, we'll be transitioning stage 1 to helium. And I'm receiving an update here. We just got the data from our latest weather balloon, and we are a go with upper level winds. The weather isn't stopping us today.
Stage 1 pneumatics have transitioned to helium.
And that means we're pressurizing the propellant tanks to flight pressures with helium. As a reminder, during flight,
for engine chill.
We'll pressurize the tanks with autogenous pressurization. That last call out was that we're pressurizing the tanks for engine chill.
We're now getting into the business end of today's countdown. Let's take a moment to walk through the launch timeline.
At T-minus 3 minutes, the transporter erector, or that black truss structure, will retract just a few degrees to give the proper angle for umbilical separation. At this point, the vehicle will be on internal power. Then at T-minus 70 seconds, the vehicle will go into terminal count. This is again when the vehicle's internal flight computer takes control of the countdown. And we then go into final flight termination checks
Igniters and flight targets.
and get FTS go from the launch conductor in coordination with the mission flight control officer and operations safety manager. At T-minus 6 seconds, we'll have ignition of those 9 beautiful 3D printed Aeon 1 engines, so you'll see the flames beneath the rocket at that point. And at T0, we will have liftoff. Shortly after that, at T plus 2 seconds, the strong back will throw back to assist in removing the umbilicals and clear the path for the vehicle to fly. At T plus 12 seconds, we'll begin our pitch over program. And at T plus 80 seconds is that important milestone of max Q, or the point of maximum dynamic pressure. This is again where the structural loads on the vehicle are the highest, making it one of the more challenging phases of flight.
At approximately T plus 160 seconds, we will get to main engine cutoff, or MECO. This is when the stage 1 engines will shut off. This will be followed shortly by stage separation and ignition of the Aeon vacuum engine. Second stage will burn for a little under 5 minutes, and then at approximately T plus 463 seconds, we'll have second engine cutoff, or SECO. As a reminder, we do not have a fairing or any payload deployments for today's first launch. We'll go ahead and continue listening in on mission control.
We're currently priming the igniters with gaseous oxygen and gaseous hydrogen. Our ignition system uses these propellants flowing across the glow plug.
Stage 1 igniters priming in.
Stage 2 ignited and final press.
As a reminder, GLHF is our maiden launch, so while a nominal flight would have Terran 1 reach orbit today, our primary goal is to learn as much as we can and demonstrate the product concept. A major milestone would be to have Terran 1 make it through max Q, the point of maximum dynamic pressure.
Stage 2 is on internal power.
And you'll now see those cradle arms are slowly starting to release stage 2 at the top there so that the strong back can retract.
Stage 1 TVC checkups.
Over the next minute and a half, we'll be performing the final thrust vector control health checks on both stages before liftoff. You'll be able to see the engines gimbaling or tilting if we're in that engine view. There we go.
Stage 1 is on internal power. Strong back retracting.
And now that black truss structure behind the vehicle will retract just a few degrees to prepare for umbilical separation.
Stage 2 TVC checkups.
As we approach T-minus 2 minutes, what you're looking at on your screen is a vehicle that is 85% 3D printed, and it is about to fly. Next up, our range coordinator will ask the range for their final green status.
Hold. As the MIFCA will hold due to a fouled range.
You heard that call out. Someone is calling a hold due to the range. We're going to stand by for updates. appears that there may be a vessel within our clear radius. We're going to stand by to hear confirmation from the range. And I just got confirmation there is a boat in the range. We're going to stand by to see if they can clear the boat from our radius. Once again, just to clarify, our vehicle is healthy and all systems appear to be performing nominal. We just got to go for the weather for upper level winds, but unfortunately there's currently a boat in the range, so we're just awaiting confirmation to see if they can clear that boat in time and get it out of our radius.
Announcement on countdown nav is the LD. We got a hold called prior to terminal count. Hold gating items have been cleared. We are adjusting for a new T0 time. We'll hold the clock for terminal count until we pick up the count.
All right, now we are just confirming a new launch time. All items that were blocking us and giving us a red range have now been cleared out. So we're going to await that updated launch time and then update the T clock above as necessary. All right, and the clock is about to resume just shortly here. They are coordinating that new T0. We're very excited to get this thing
Now
going.
countdown net. T-clock should pick up in 60 seconds.
60 seconds. We have confirmed our new T0 is going to be 14:42 Eastern. Once again, that's 14:42. We'll see the T-clock rolling in just a moment here.
T-clock's rolling. Terminal count.
Colin Dalton, close out.
Flight computer and countdown.
T-minus 60. GCU with the count. LD, are you go for launch? LD is go for launch.
And we just got that final go for launch from our launch director. We are now just about...
Range green.
Range is green. We're now about 30 seconds away from the moment that we've all worked so hard for our first launch. We've had a lot of fun with you, Terran 1. Good luck. And here we go.
Ten, 9, 8, 7, 6, 5,
As you can see, we had ignition of our engines, but the T-clock did hold at T0. We're going to stand by for updates. All right, I'm hearing from Mission Control that we're currently assessing vehicle health to confirm if we can do a recycle today and try this thing one more time.
Announcement on countdown net. This is the LD. The aborted terminal count on a launch commit criteria violation at T-minus 0.5 seconds prior to liftoff. Are safe in the vehicle and assessing recycle opportunities.
As you heard, once again, we had a violation with our launch commit criteria, which is why we had an abort shortly before liftoff. The team is continuing to assess vehicle health to confirm if we can have a recycle today. As a reminder, we're currently at 14:50 Eastern Time, and our launch window is open until 1600 Eastern. So our teams are currently assessing any recycle opportunities that we have during this time. You'll see an occasional cloud coming out of the transporter erector or the black truss structure there. That is just because we're keeping our propellant topped in case we can re-attempt a launch before the end of the window today at 4 p.m. Eastern. As you can see, the T clock rolled back. We are still working on a recycle, so we'll keep you updated as soon as we have confirmation. The T clock is rolling again, everyone. We just have an updated launch time of 15:55 Eastern. Once again, 15:55 Eastern in just under 44 minutes. We're going to keep going. I just got an update from our engineers and mission control. We are updating the T0 time to 1600 Eastern. Once again, that is 1600 Eastern. T-clock is rolling.
For those of you that are tuning in today, we're going to take a moment again to introduce ourselves. My name is Rachelle Aniceto. I am the Chief of Staff for the Vehicle Architecture and Technology team.
And I'm Arwa Tazani Kelly, Technical Program Manager for Test and Launch here at Relativity Space. Now, ahead of Terran 1's liftoff, we invited some of the most influential voices in the space industry to curate some questions from you all on Twitter about our journey to launch. We appreciate the time that Michael Sheets, space reporter at CNBC, Eric Berger, senior space editor at Ars Technica, and Tim Dodd, the everyday astronaut, took to answer your questions. Let's take a look.
This question comes off of Twitter from Danny Stover. Many launch companies fail their first attempt. Will Terran 1 reach the same fate? What makes Relativity's approach different? I want to hear, Michael, what do you have for that one?
Many companies failing their first launch attempt is, I think, a great example of the high risk aspect of the development process. And I think that's one thing a lot of people need to keep in mind is there's along the way to development, even before launch, there's all these milestones that you're trying to get through, including, as we've seen recently, static fire. So you pass those milestones, you get more data. As you move closer and closer, the end goal is, can we not just get into space, not just get into orbit, but deliver into the targeted orbit, get to the place we want to actually be? And I think a nice analogy of it is like ordering an Uber. You want an Uber that's going to get you the closest to your destination, ideally your front door. But if your Uber is dropping you off, a couple miles away, you're probably not going to continue, using the app anymore because you're going to try to go with a competitor who's actually getting into that ideal orbit. So will it make its first attempt is that open question. And I think I really want to stress the development side of where the company is, because people see failure at kind of any stage and they go, oh, this is a wash. But it's really important to understand that ultimate goal of an intentional specific orbit.
I'll answer the question a little bit more bluntly. I do think Relativity probably will fail on their first launch attempt. If you look back at no new space company has ever reached orbit on their first flight attempt. You had Rocket Lab fail, SpaceX failed on their first attempt, Virgin Orbit failed, Firefly failed, ABL failed, and so it's the odds are against them, and more credit to them if they succeed. And I also think that the 3D printed nature of the structure is a big test. Are you going to be able to see that get through max Q? And then there's some more complex elements on the Terran 1 rocket that you might see in a more traditionally developed launch vehicle. And so I think seeing a nominal first stage performance would be a pretty big win for Relativity. And I'd love to see them get to orbit on their first time out. I just think historically the odds are pretty long against it.
Yeah, I'm definitely with Eric there. I realized just recently that, the Pegasus, when it first launched, was one of the only rockets to successfully make it to orbit on its first launch. So, that was definitely not by any means considered new space by today's standards. But realistically, like Eric said, the odds of being completely successful on the first round is statistically about zero. So I'm just excited to see if they can get through the first big milestone. If they can, make it through max Q, if they can see stage separation. Each staging event is definitely one of those big unknowns until you do it for the first time. Can you light your upper stage engine? Can you, deploy your fairing? Can you eventually, if you get to deploying a spacecraft from, on orbit, that's the ultimate milestone, of course. But yeah, there's a lot of things between there and leaving the ground. So yeah, time will tell.
I think only of the companies that we talked about outside of Pegasus, and that was Orbital Sciences, and of course that was a solid fueled rocket, and most of which was not developed in-house like the commercial space companies of today. But, of the companies we talked about, only Rocket Lab got to like a second stage engine ignition and flight, right, on their first mission?
Yeah, 21st century wise, that's definitely true. And I think another way to tackle this question is defining failure, because, when you talk about many companies fail their first attempt, you need to understand the multi-step process of a rocket launch. And I think that's another important aspect where depending on how far they get towards their ultimate goal, will categorize whether this is a learning experience from a failure standpoint or this has a lot more to build upon. And every step that they complete during the launch is another check mark towards success.
Yeah, absolutely.
This next question comes from Hantronics. With the capability of 3D rocket printing, will we see a day when rocket engines are a part of the ship structure such that their major components won't need to be removed, inspected, or replaced after every launch? I don't remove my engine in the car every 1,000 miles.
I think there's always going to need to be some kind of repairability and separateness of the components of the structure of the vehicle and the engines. I mean, there's just an inherent physical moving parts. You have bearings, you have valves, you have components that just would need to be inspected on any vehicle. And if you completely integrate that into the structure to the point of not being able to remove and service it, you just really, you really limit yourself. Now, if you're talking about an expendable launch vehicle, there is the potential that integrating it could actually add potentially some reliability or simplicity or mass savings. So it depends on your overall goal. If you're talking about a reusable vehicle that you're flying over and over and over, completely integrating it to the point of not being able to even remove and service it is probably not the best idea, in my opinion.
I would just say that, this is an impossible question to answer now because we have to see if 3D printed rockets are capable of flying. And that's the great thing. What I love about the launch industry today is you've got all these companies trying different things, right? You've got ABL out there trying to basically build a miniature Falcon 9 as simple as possible, a modular approach, ship it and shoot it from a launch pad. You have, Virgin Orbit trying air launch. You had Astra trying to build the cheapest, perhaps less reliable rocket. And you got Relativity doing additive manufacturing. And so it's great to see all of these different approaches because, we're going to try them all out. And it takes a real world test, I think, to get the right answer ultimately.
I'll do this one. This one comes from Kyle A. Mame asking, what other markets in the space sector or beyond do you see Stargate technology being applied in? I kind of mentioned it earlier. I would love to see, large scale additive manufacturing be used for, automobile prototyping, race car prototyping, especially. Oh my God, like the Formula One world where every year the cars have new restrictions and new rules and a new, set of rules to have to engineer by. Being able to at scale develop stuff with a 3D printer makes all the sense in the world. So I think that's a pretty no-brainer to be the automotive industry.
I think there certainly are potential other market use cases, but additive manufacturing, obviously predated Relativity, and they're trying to apply it in this really significant way with such enormous structures. And I think that's the fascinating aspect is you try out the technology behind the rocket in such a extreme use case where then other sectors can look, where can we apply this? Where can we iterate faster by implementing printing these as solid entire structures as opposed to different pieces that you put into whether it's for shipping or other large industrial components. You can see the kind of downstream effects of basically a demonstration of, hey, we can build a rocket with this type of technology. What else can't we build?
I think Michael's exactly right. There's been talk about Relativity since it was, almost since it was founded. Is this a launch company or is this a 3D printing company? I think, that once they sort of wrap their hands around spaceflight, they're going to be taking this technology into other areas. And we don't really know what those are. It'd be interesting to find out. Just for me personally, one of the big issues that we've seen in this country and around the world has been housing issues. And so I don't know if 3D printing these large structures could be applied to housing units or things like that. But it's going to be fun to find out where this technology goes.
That was a great video answering some of your questions on Twitter. Now we are at T-minus less than 30 minutes from our launch with our updated launch T0 time of 4:00 p.m. Eastern. So that is 1600 Eastern. We're currently going to stand by from an update from Mission Control in the next few minutes. The go, no-go polling from Mission Control is coming up here in just a couple of minutes, around T-minus 16 minutes. We're going to stand by and continue listening in, awaiting that poll.
All parties, all nets. This is the go, no-go poll for launch. Please provide concurrence for proceeding to launch operations with go, no-go. GC go. GNC. Flight software. Prop 1. Prop 2. Fluids 1. Fluids 2. Loads. Rock.
Ranges go.
OSM. RC.
RC go.
Vehicle. CE. LC. LC go. All parties report go for launch countdown.
All right, our team is being relentless here. We are not giving up, and we're going to give this one more shot with an instantaneous window at 1400 Eastern. As you heard, all parties have reported they are go for launch.
And just a reminder, 1600 for that launch. And as we continue to wait, let's remind you what we have inside of our nose cone. So we don't have a customer payload on board, but we do have our special Memento, which is our first ever 3D printed piece from our Stargate printer. As we mentioned before, it was a failed print, but this is just special for us as we get to this moment. As a reminder, that piece is about 6.5 inches in diameter and weighs about 3 pounds, and it is our first completed circular test article for which we used our first generation aluminum alloy. Since then, we added a machined centerpiece with GLHF and our mitosis logo to commemorate this maiden launch. We'll go ahead and tune back in to mission control and wait as we get closer and closer to launch.
T-minus 10 minutes, countdown sequence has started.
And you heard that call out. We're currently at under T-minus 10 minutes. And in the upcoming minutes, once again, you're going to hear several call outs from Mission Control as we go through the final pre-launch procedural steps, including priming of the igniters, final engine checkouts, transporter erection retraction, and getting that final go for launch for this attempt. Again, we're now pressing the tanks
to flight targets.
To flight pressures, as you just heard, and we're currently proceeding with our time of 1600 Eastern. This will be our last attempt for today, and it is an instantaneous launch window. Stage 1 will be transitioning to helium shortly.
Stage 1 pneumatics have transitioned to helium.
Once again, that means we're pressurizing the propellant tanks to flight pressures with helium. And as a reminder, during flight, we'll be pressurizing using autogenous pressurization. Tanks are pressing for engine chill.
Since we're getting into the business end, let's remind you about our launch timeline. Arwa, take it away.
So again, at T-minus 3 minutes, the transporter erector or the black truss structure behind the vehicle is going to retract just a few degrees to give the proper angle for umbilical separation. At this point, the vehicle will of course be on internal power. At T-minus 70 seconds,
Stage 2 igniter for flight targets.
The vehicle will go into terminal count, and this is again when the vehicle's internal flight computer takes control of the countdown. We'll then go into flight termination checks and get FTS go from the launch conductor in coordination with the mission flight control officer and operations safety manager. At T-minus 6, we're going to see that ignition one more time of those 9 Aeon 1 engines. So you'll see the flames, the blue fire, I should say, beneath the rocket.
Stage 2 igniters priming in.
And at T0, we'll have liftoff. At T plus 2 seconds, the strong back is going to throw back to remove the umbilicals and clear the path for the vehicle to fly. At T plus 12 seconds, we'll begin our pitch over program. And then at T plus 80 seconds, we're going to reach max Q, or the point of maximum dynamic pressure. This is again where the structural loads on the vehicle are the highest, making it one of the more challenging phases of flight.
At approximately T plus 160 seconds, we will get to main engine cutoff. That is where the stage 1 engines will shut off, and it will be followed shortly by stage separation and Aeon vacuum engine ignition. Our second stage will burn for a little under 5 minutes. Then at approximately T plus 463 seconds, we'll get to second engine cutoff when that Aeon vacuum engine will shut off. And as a reminder, we do not have a fairing or any payload deployments for today's first launch. With that, we'll go ahead and sit back and listen back to Mission Control.
We're currently priming the igniters with gaseous oxygen and gaseous hydrogen. Again, our ignition system uses these propellants flowing across a glow plug. Less than 5 minutes away.
Stage 1 igniters priming in.
GLHF again is our maiden launch. So a nominal flight would have Terran 1 reach orbit today, but our main goal is to learn as much as we can about this vehicle and demonstrate the product concept. A major milestone would be for us to reach max Q today, the point of maximum dynamic pressure.
Stage 2 is on internal power.
And the TE
cradle disengaged.
TE cradle, there we go, disengaged. You'll see that cradle arm slowly start releasing stage 2 so that the strong back can retract. And you can see the engines gimbaling there. We're performing the final thrust vector control health checks on both stages right before liftoff. You can see stage 1
is on internal power.
Engines there.
Strung back retracting.
And now that black truss structure will retract just a few degrees to prepare for umbilical separation. There it goes.
Stage 2 TVC checkout.
As we approach T-minus 2 minutes, just a reminder, the vehicle you're looking at is 85% 3D printed. Those white clouds you see coming out of the rocket are due to the venting of the chilled gas from the vehicle into the humid air that we have here in Florida. That's why it condenses into vapor and it looks like clouds that are floating out. You'll also see the flare stack on the bottom right there. That is just used to vent out flammable gases. Next up, our range coordinator will ask the range for their final status.
Rock, report range status.
Range green.
We got confirmation. Range is green for launch.
Propellant topping closeout.
Flight computer and countdown.
Final countdown, that is the LD. We've had a board and terminal count. This is a final instantaneous T0 launch window. We are going to be scrubbed for the day. Safety of the vehicle. Thanks for playing.
Our teams obviously gave it an amazing shot today, and we had high hopes for sending our Terran 1 off, but we're going to continue to take a measured approach so we can ultimately see this rocket off to max Q and beyond.
Once we have an update on the timing of our next launch attempt, we will share that via Twitter at Relativity Space. We hope you will join us again soon to see the world's first 3D printed rocket fly. I am Rachelle Aniceto.
And I'm Arwa Tizani Kelly. Thank you. See you next time.